Video 2E, Fitting Data to a Line. This video explains using the most common technique for fitting a line to a data set and for estimating the errors in the line parameters and the spread of the data. Many data sets are assumed to have linear or largely linear behavior with some superimposed noise. If we make a set of measurements and we assume there's a linear relationship between the independent values and the dependent measurements, we need to perform a linear regression on the measurements and report the slope and intercept with their uncertainties. We probably also want to plot the data, the best fit line, and the confidence interval on both the line and on the data. With the advent of amazingly powerful computers, there are lots of line fitting techniques to use. The most common one is still linear least squares, and so that's what we'll use here. You are free to use the others in your report as long as you state what you're using and why, and also use them correctly. For a set of n measurement pairs, x1 through y1 through xn, yn, we assume a linear functional relationship where the ith value of y is equal to the true intercept beta naught plus the true slope beta 1 times the ith value of x plus the error in the ith value of y. We're assuming that all of the error is in y and none in x, or that the uncertainty in x is much smaller than the uncertainty in y. If we knew the true or noiseless value of y, beta naught and beta 1, we could calculate the true error as either y sub I minus y sub I true, or y sub I minus the quantity beta naught plus beta 1 times x sub I. However, we don't know any of these, so we're going to work as before with estimates and residuals. The residual of point sub I is either y sub I minus y hat sub I, or y sub I minus the quantity beta hat naught plus beta hat 1 times x sub I. The hats or circumflexes indicate estimated values, just like x bar is an estimate from u. We will sum the squares of the residuals and then minimize the sum by varying beta hat naught and beta hat 1. The symbol for the sum of squared residuals is SSE, which may, I suspect, reflect a casualness about the distinction between residuals and errors. We're not going to do it, but you minimize SSE by taking the derivative of SSE with respect to both beta hat naught and beta hat 1, setting the derivatives to 0 and solving for beta hat naught and beta hat 1. The results are given here, with x bar and y bar being the usual arithmetic mean of the x sub I and the y sub I. There are several mathematically equivalent forms for calculating beta hat 1, so don't freak out if you don't like this form. How good are our estimates of intercept and slope? We'll follow the procedure similar to that for determining how good an estimate for mu x bar was. We'll start by calculating the root mean squared residual, or RMSE, or S sub E. It is calculated as the square root of SSE over n minus 2. You'll notice the similarity to the sample standard deviation, but the denominator is n minus 2 instead of n minus 1. We used both beta hat naught and beta hat 1 in calculating their RMSE, and they're both calculated from our data set, so we've lost two independent equations, or degrees of freedom, hence n minus 2. The standard error for beta hat naught has the square root of 1 over n, like the standard error for x bar, but it also has a term to account for the linear fit. The expression for the standard error for beta hat 1 just has a term for the linear fit. As before, we'll use student's t-value for correcting for the desired confidence level. When we look up t, we need to use n minus 2 as the degrees of freedom for the reasons given before. The reporting format is exactly the same as for the mean with confidence interval and confidence level. One way to think about what we're doing is to consider setting the independent variable x in our experiment to some value and taking repeated measurements of y. The results would be a histogram of y values. We could fit a normal distribution to that histogram and calculate the mean and standard deviation. From these, we could calculate the confidence interval for the mean of the data as we did for measurements of a single variable. Likewise, if we wanted the bounds where some confidence level of data points would be contained in the histogram, we would multiply the standard deviation by t for that confidence level. If we did these measurements and calculations for multiple x's, in this case 11 different x's, we would have histograms that have the same shape more or less, but whose mean varied linearly with x. In addition, the line showing the mean versus x, we could plot the lower and upper confidence bounds for the mean and the lower and upper confidence bounds for the data. If we view the histogram from above, we can see the lines for the mean, the best fit line, and the lower and upper confidence bounds for the best fit line and the data. For your reference, MATLAB refers to these as functional bounds and the observational bounds respectively. To calculate the confidence bounds on the line or the mean, the functional bound, we need the standard error on the mean or the y value. The standard error on y for a given x is displayed here. It differs from the beta hat naught standard error in that it replaces x bar squared with x minus x bar quantity squared. As before, the confidence interval is students t times s sub y hat. We would plot the upper confidence limit for the best fit line by plotting beta hat naught plus beta hat 1 times x plus lambda sub y hat as a function of x, and the lower confidence limit by plotting beta hat naught plus beta hat 1 times x minus lambda sub y hat as a function of x. To do the same calculations on the data, the observational bound, we need to add a 1 under the radical. The relationship for the confidence interval and the upper and lower confidence bounds are analogous to the functional bound cases. It's important to note that in all cases, the standard errors and hence the confidence bounds are functions of x. In case you hadn't noticed, we're not deriving the formulas, just giving the results of the derivations. If you're curious, consult a statistics text or search the web. Let's do an example. A fictitious dean at a fictitious liberal arts STEM college randomly queried 5 students who happened to be outside of Starbucks what their average sleep was per night and then matched them against their GPAs. The data look as follows. Let's do a linear fit to the data and figure out the range of GPAs for students who sleep 7 hours a night with an 80% confidence level. Then let's plot both the bounds on the mean and the bounds on the data. The formula requires x bar and y bar, which calculate out to 6.1 hours of sleep and a GPA of 3.36. From these, the best fit slope, beta hat 1, is 0.183, and the intercept, beta hat naught, is 2.238. The root mean squared residual is 0.136, and the standard errors are 0.0407 and 0.255 respectively. The student's t-value for 3 degrees of freedom and 80% confidence is 1.638, giving a beta hat naught of 2.238 plus or minus 0.148 with 80% confidence, and a beta hat 1 of 0.182 plus or minus 0.067 with 80% confidence. Here is the plot with the data points, the best fit line, and the confidence interval. As to our student who sleeps 7 hours a night, y at x equals 7 is 3.52. S sub y is 0.154, and t is still 1.638. So plus or minus lambda sub y is 3.27 to 3.77, which we also could have read off the graph. What are the implications of all of this on your measurement making? If your relationship is truly linear, you can make the confidence limits on your fit arbitrarily precise by taking a large number of measurements. However, limits of time and money mean that the number of measurements you make has to be limited. What are the trade-offs? The confidence interval lambda is the product of students t and the standard error. For a given confidence level, t decreases asymptotically. And as before, the decrease in t and hence the confidence interval from 3 measurements to 4 is by far the largest, which implies that when fitting a 2-parameter curve, take at least 4 data points. Beyond 4 points, the increase in accuracy due to the decrease in t exhibits the law of diminishing returns. The effect of increasing n on the standard error is more complex than for the 1-parameter case, but roughly speaking, for each 100-fold increase in the number of points, you have a 10-fold decrease in the confidence interval. You as the engineer need to decide how much accuracy you need given how long it takes to do a measurement. To illustrate these points, this next video displays the data points as black X's, the best fit line in red, the 95% confidence bounds for the mean or line in blue, those are the functional bounds, and the 95% confidence bounds for the data in magenta, those are the observational bounds, as we add additional measurements beginning at 3 and ending at 250. The true standard deviation is set at 1. Note how large the confidence intervals are for 3 measurements and how rapidly they decrease for 4, 5, and 6 measurements. The data confidence bounds show quite a bit of derivation for a small number of points. The data confidence bounds show quite a bit of deviation for a small number of points, but become quite stable as the number of samples increases. In addition, the functional and observational bound curves become less and less curved and closer to straight lines as the number of observations increases. As we mentioned above, you can make the confidence intervals on the function arbitrarily small by adding the number of points. We will see shortly the result of 250 points. The takeaways from this video are: 1. When fitting a line to data, make at least 4 measurements, which gives you the greatest decrease in uncertainty per additional measurement. 2. Do not use the methods in this video by hand to calculate your best fit line and confidence bounds. Use a software package to do it for you. 3. Report your results with the best fit values for your measurements, the confidence interval, and the confidence level. For example, beta 0 is 2.238 plus or minus 0.418, and beta 1 is 0.183 plus or minus 0.067, both at an 80% confidence level. 4. Plot your data with the best fit curve and the mean confidence bound, and possibly the date of confidence bound, depending on what you want to convey. There is not a video for performing these calculations by hand. Hand calculations for a large set of data points are tedious and error-prone. There is a video on using a spreadsheet. Spreadsheet calculations are not too bad, and there are some built-in functions to help. There is an additional video for performing these calculations using MATLAB, which is probably the best tool to use of the ones we typically use in E80.